All right, I'll do the rest of it in English because my Swedish is okay, but not really good enough to get across what I want to do. So very happy to talk to you all. My name is Alex Bock. I'm a lecturer here at the university and also the head of unit for all research that comes across that immersive visualizations. So that means anything that is happening over in the dome, in the visualization center, but also VR headsets and all kinds of environments that are surrounding you, like that is getting luckily more and more common these days. So I'm here to talk to you about one of our projects that we've been working on for a very long time that I started doing my PhD, which is called OpenSpace, which is the short version of it. It's a game engine without all of that pesky game part. It's all but with real data instead. And the nice thing is that it's all open source. So everything that I'm talking about, and I'm going to do a little demo about as well, like everything of that is available for free to download for everyone to play around with, throw in new data sets, whatever you want to do with it. We're very eager to see whatever we can do with these tools. So the slightly longer version of that, and I'm not going to go through all of it because it's way too much text, but the first line describes it in a very unintuitive way. So it's a large scale, means we're doing that in large environments, but also large scale in content. Contextualized, which means we want to show different data sets in their proper context. So for example, if you want to look at let's say a satellite, it's like, if not really knowing where that satellite is and which orbit is orbiting, it doesn't really make much sense to just look at it in like without the proper context. And then multi-model, we want to show multiple data sets at the same time. And then astrovisualization, I think that one's pretty clear. And then it's a game engine. So the interesting part is really at the bottom, this exploration, explanation, because that's the thing that we started pioneering here in Norrköping, of this combination of explorative data, which means you go into an exhibition and just look at something that has already been discovered and rediscover it, like looking at, let's say, a touch table interface and looking at what kind of bodies are there, whatever. Like, and then the explanation part is like the whole public outreach part, and we combined this into a new concept. But the software itself, it's running on a bunch of different planetariums, including the one here in Norrköping, and it's also used basically all across the world. So we got a couple of hundred people that are using it daily. But the thing that I really want to bring across, and is one of my probably favorite slides in the whole world, which gets the point of the software across better than anything else, is this one. So a couple of years ago, we had an exhibition in New York where we basically put up a laptop with a screen in a park and had an Xbox game controller. And everyone could just come up, start flying around on Mars or wherever they wanted to go. So we have this little boy here that is just doing that. So he's exploring this planet for the very first time for him. About 2 weeks later, we were in the Hayden Planetarium in New York, which is bigger than ours, but I don't think it's as good. Oh, damn, we're being recorded. So it's really good. So we were there like looking at exactly the same software, just with different data sets. So the person that we have lying here on the ground, his name is Jack Mustard. He's from Brown University. So he's on the Perseverance science definition team. So he's on the team that decided where that rover was going to land. So he's lying here on the ground, looking at the same software with just slightly different data sets. So this combination is kind of what's at the heart of all of this. So that's why I want to bring in the combination of education and science. We can do the education of the future people in being interested in space, maybe studying something that's technology related, maybe not, but that doesn't really matter. Getting people excited about space and learning. And then on the other hand, we have people that want to do the scientific discovery all by themselves. And if we can do that in the same software, we kind of cross-fertilize these kind of different fields, and everyone's off better for it. So the software is a collaboration between us here at Linköping University, where it started, and the American Museum of Natural History in New York. And then NASA Goddard Space Flight Center outside of Washington, New York University, and the University of Utah. So we've got partners from sitting all over there. And I'm not going to bore you with too many pictures, but these are some of the administrative people at the top and some of the students at the bottom who are doing their final year projects within the software. So a lot of the stuff, and this is another one of the points that I want to bring across, is a lot of the stuff is actually developed by students in their final year projects. So if I now highlight all of the people that have come from the media technology course here at the university, So it's like the overwhelming majority of people that have developed things have learned how to code and how to design things at the university. So it's like, with everything I'm going to show, it's like it might look quite impressive, but it's all built on top of people that were in their learning phase of things. So just because something looks impressive doesn't mean that you can't do it. So that's probably the other big point that I want to get across. It's like, try to look under the hood of things and try to break things, and that's usually a good thing if you can set it back. But trying things out and just learning is what we're all about. So all of the developers are all situated around the globe. And so within the software, and I'm going to do a demo very quickly just to keep it interesting, we have this idea of having 3 different users for the software. One of them is our users. So those are people that hopefully, like some of you, will download the software, start exploring it for yourself, learn something new about the universe, maybe about planet Earth, and then basically be able to tell a story about that, like Rachel is doing here. Then one step further down, because it's all open source, we can have these groups of builders, which are people that take what's already there and just rejiggering it a bit and tell something completely new. Let's say we put in a new spacecraft, or we put in new maps of Earth, like how carbon dioxide is moving around the planet, for example. Like all of those data, they're all available and free. Like, because a lot of the stuff is done by US institutions, which are tax funded. Almost everything they're doing is available for free for downloading. You just have to find it, which is usually the hardest part, but then once you have it, you can do with it whatever you want. Like, the world's your oyster. Like, there's a lot of oysters out there. And then lastly, we have the developers that are basically doing the C++ coding to actually make the engine work. So one of the examples that we have is using it for astronomy research. So in this case, this is one of the research projects that 4 of our students were working on. So the colorful blob on the left, that's the sun, and the sun periodically sends out huge amounts of plasma into space. Some of them hit Earth. Some of them, when they get trapped around Earth, they end up being the northern lights and the southern lights. So those particles that end up glowing nice and green start out on the surface of the sun. So our collaboration partners, they were doing simulations of the sun. So how does the sun actually behave? So we were getting, this is from a YouTube stream that we did together with them. So we can see, like, now within the software how these enormous clouds of plasma just burst out from the sun and how they propagate through the solar system and how they impact us. Another one is the Gaia dataset, it's a spacecraft that has been orbiting or has been flying around for a couple of years now, and it's a European Space Agency project that has been mapping the night sky to unprecedented detail. So before this spacecraft, we knew of about maybe 100,000 stars in our galaxy, which is, I mean, a lot. But now that this spacecraft has been operating for a couple of years, this number has gone up to 1.7 billion stars. So those are all of the individual dots that you see there. Those are all stars that we collectively as humanity have mapped. We know the location of them in the night sky, and we also know their 3D position. So we can fly around them, look where they're going, and do new discoveries in here. And then, of course, because my hat is a visualization researcher, like, there's a lot of research that is going on just to make all of these things happen. But that's where the student research is coming in as well. And then finally, particularly here in the Visualization Center, very regularly we do live dome shows that are using the same kind of software that I'm going to run on this laptop, just in a planetarium, and being able to do an interactive show. So the thing is, it's not a movie. Like, a lot of people get that wrong when they come into the dome, but it's not. It's essentially a game. Like, we decide as a group where we want to go. It's not pre-rendered. It's interactive. Like, it demands of the presenter to know a lot more, but it's also much more engaging, I would wager. So just one of the examples that I want to bring up is one of the people that we're working with. His name is James. He's in New York. So that's his planetarium. So during his kind of COVID project was to start making Instagram videos for using OpenSpace, and he's been quite successful with that. So these are two of the most popular ones that he has. So both of them are somewhat north of 12 million views by now, which is basically showing the movement of the sun. One of them from the surface of the Earth. So you see, like, as the year progresses, the location of the sun is moving over the night sky and doing this what's called the analemma figure. And this figure is going to be looking different wherever you are on Earth. Like, if you're at the North Pole, that figure 8 is going to be looking very flat. If you're down at the equator, that one's exactly straight up. And the angle of this figure 8, you can calculate, if you really want to, where he was at that time to do that. And it's like, this is like a nice way of like experimenting and seeing like how can we use all of this information. There's a bunch of other examples that are all really interesting, but let's do some demo instead. Okay, so now I'm loading the software here on my laptop. The battery is still pretty dead, so it might be not running at full speed, but we'll see. And I'll just bring down the light a bit so we can see a bit better. Now everything's very small. So now we're running this interactively. So that's not small enough. That's not too small. Now this is getting really awkward with a stick mic. But now this is all interactive. So we're running this as we are with current data. So this is how Earth looked like yesterday. I'm not sure, a lot of people here didn't really notice that, but 2 days ago there was a partial solar eclipse that passed over Sweden. I'm not sure if anyone noticed that? One? Cool. So we could, for example, ask, like, how did it actually look like if we look at it from space? So now we're on October 27th. If we go back one day, now we're downloading the new data sets from yesterday, and I think we have to go one more day back because it's actually 2 days. So you see like this little dark strip over here? That is actually where the satellite was taking its pictures as the solar eclipse was happening. So that's why it's darker. So that's one of the things that we try to do. Is like, we don't try to fill in anything. We'll just show it exactly as it is. And as you could probably see as well, like if we go, I think it was around 12 o'clock if I remember correctly. Yep. So there we see, let's move a bit faster. You can see the actual shadow of the moon just grazing Earth. And that's why it's a partial eclipse. The center of the shadow was not on Earth. It was just like in the boundary layer. Because like if you have ever seen a total solar eclipse, that one no one would have ever missed. That one I can guarantee. But now, for instance, we can have a look at, there's this purple line that you probably saw. Let's bring it into something more nice. So that one is the International Space Station. So that one we have two, so we can refocus our camera. And if we start zooming in, start loading more data in the background, and after quite a bit of zooming in, we can see where was the International Space Station on October 25th at 1838. And this is exactly where it was. So we can compare that with the actual location, the information that we get, and like, well, we get our location data from there, so obviously it's going to match. And we can do this with a lot of different data sets and just look at them in context, because I think everyone has probably seen pictures of the ISS, but not necessarily how Earth looks like from that, because it's not like flying high in an airplane. It's like you can actually see the curvature of the Earth from the 420-ish kilometers high up over the Earth. So let's look at something else. So while we're looking at Earth, so we've sent out like a bunch of different things. So the ISS is one of them, but then we have sent out other satellites. So one of them that I'm going to bring up now is called the 100 brightest ones. So those are the 100 objects in the night sky that are most easily visible from the surface. So when you're out at night or like in the evenings times, sometimes like if you notice that there's like a very bright streak like just going across the sky very quickly. So that is very likely one of these satellites. This is not looking very good, so it's all interactive, so we can just Let's make it a bit more cyan colored. And now we can also play around with time again, so we can start animating time and seeing how all of those 100 satellites are actually in their correct position around the sky. So you could technically use this to predict when there is going to be one of those streaks going across by just looking at the planet. Well, in this case, we're looking for Norrköping, looking up from Norrköping. When it comes to satellites, these ones are not, these ones look nice, but they're not super interesting. One of the other ones that I guarantee that almost every one of you is using essentially daily these days is what's called the GPS navigation satellites. So whenever you open up Google Maps or Apple Maps or whatever, try to figure out where you are, your phone is communicating with mostly 4, sometimes more, different satellites out in space to figure out where you are. The math behind all of that is quite complicated. It is all something to do with the satellites are sending out radio signals. Radio signals travel at the speed of light, so it takes them a finite amount of time to get to us. And that time is different for each of the satellites because they're in a different place. By calculating the differences between those two, your phone can figure out where you are on the surface of Earth, which, I think it's fascinating that we've been able to figure that out. But then also, if we look at the actual GPS satellites, remember where we were before? So the GPS satellites, they're orbiting out here. So each one of those streaks is one of the GPS satellites that your phone is communicating with when you're trying to figure out where you are in a city, or if you take a picture and that picture has the geolocation baked into it. That information came from out here. And then lastly, which has lost quite in significance in the recent years, is what we call the geostationary satellites. So those are satellites that have a very interesting attribute, which means that they orbit around Earth once every 24 hours. As you probably know, Earth rotates once around its axis every 24 hours. So that means that those satellites are staying in the same relative position towards Earth, from Earth. So as Earth is rotating, if something else is rotating at the same speed as me, it's always going to stay in the same relative position to me. So that means, for example, if you're seeing a satellite dish out there, that's why these satellite dishes for old satellite TV, they don't have to move. You just set them up, you point them in one direction, and then you hopefully never have to touch them again. The reason why that is working is because these satellites are orbiting at precisely this location, which is around 36,000 kilometers away from Earth. If they would be closer, you would have to constantly adjust the satellite dish. If they're further away, have to do the same thing. And we saw this analemma figure, so they would be basically doing exactly that, but they're not. They're exactly the right position from us. But I was saying it's about astronomy, so let's zoom out. We're passed by the moon, so we can have a look at the entire solar system. So Earth, well, we have people living on Earth, obviously. We have the ISS, where we have been living for the last 24 years. We have been to the moon, and the next goal that we want to get to is Mars. So let's just do that. So just as we have a lot of information about the Earth, we also have a lot of information about Mars. That is a very good question. There have been, I lost track. Oh, sorry. The question was if there's water on Mars. I lost track the amount of times that people have claimed that there's water on Mars. I mean, it's very unlikely that there isn't water on Mars because water is everywhere. But at least at the equator, we haven't found any traces of liquid water. There seems to be water that is in the ground, seeped up in the ground. But yeah. So we haven't seen it yet. Yet being the operative word, but I think it's fairly likely that we will. So here we have Mars. If I rotate the planet around a bit more, we can see, first of all, over here, the little black spot. Let's bring it a bit more into the sunlight. That one is Olympus Mons. It's the biggest mountain in the solar system. It's about the size of France in area and about 23 kilometers high. So it's like almost 3 times Mount Everest, but on the scale of France. So, and actually the reason why you're seeing it so dark is that the atmosphere of Mars is very thin. This mountain is very high, so it actually sticks out so far out of the atmosphere that it's not get colored by the atmosphere itself. So it's one of those massive formations. So Mars is a very weird place. So yeah, Olympus Mons. The other one that's really interesting is right here. It's called Condor Chasma. It stretches from roughly around here all the way around here. So this is about the size of Europe. And if you think about the Grand Canyon, if someone has seen pictures of that, it's really impressive. So this is kind of like the Grand Canyon, but the length of Europe and the altitude of Mount Everest on a planet that is about 2/3 the size of Earth. But we also have more data here. Again, as I said in the beginning, everything's free data. So what we can look at, maybe we shouldn't getting the data from Utah. Let's get them from us instead. So all of the times when you're seeing something click in, it's basically my laptop's communicating over Wi-Fi with some server somewhere. So for the last 10, 15-ish years, there's been a satellite orbiting around Mars and been taking very high-resolution pictures. So these ones, if I tick them in, there they come. So we don't have high-resolution information about Mars everywhere, so that's why you're seeing these strips. And also the satellite that is going around is going in what's called a polar orbit. So if you're thinking about the Earth, you have the North Pole and the South Pole. The satellite goes over the poles. It's a polar orbit. Like, astronomers are really bad at naming things. So that's why you're seeing all of these strips going in a north-south direction. So it is, again, one of those ways to explain how orbital mechanics works without needing to go into orbital mechanics. So if we can now start zooming in, we also have a lot of information about the surface. So as we're zooming in, we're loading in more and more data, and like the data set is, I mean, it's big, but it's not super big. Like the entire one is about 5 or 6 terabytes, so it's not like unmanageable. But now we can actually look at what another area in our solar system actually looks like. So now we're on Mars, what potential Mars astronauts in whatever it's going to be, 2035 or so, 2040 maybe, we'll see. But there's one more level, because the same satellite is also taking even higher resolution images. So if I just bring up the reading is really hard. There we go. So now what we're looking at is data that has a resolution of 25 centimeters. So every pixel covers 25 centimeters on the surface of the planet. So these mountains, they're about 50 meters in altitude maybe. So this is like the human scale. So like a football would be like 1 pixel on this. Like a car would be whatever that is, like 20 pixels or so on this image. So if we would have been here, which we of course haven't, we would be able to see footprints and everything in these images. And these are, I cannot stress this enough, all of this is free. Like, we don't have to pay for any of this. This is all, or like someone had to pay for the satellite, but afterwards it's all free, which is really cool. Okay, so for the last few minutes that I have, let's.
Alex, I think we're running out of time.
Oh, no, okay. Then just very quickly, 1 minute, because I wanted to show you everything, so I better show you everything. So while I hopefully get some questions, I'll just let it continuously zoom out, because I was saying that it's a visualization tool for the universe, so let's just zoom out. So, okay, are there any questions? That's the sun. And now we're zooming out towards our closest stars. So we have our Milky Way. So now every dot in the background is another galaxy. Those are different satellites that are taking all of that measurement. And now we're outside of the universe. So this was a very brief journey. Yes? So the question if we can do research with this, 2 yeses for the research. On the one side, we're doing visualization research with this. So the Mars surface rendering, for example, that was one of the best visualization papers in 2016 that we published about this. So the rendering behind this is one of the research. But then one of the other images that I was showing in the beginning, where we were looking at the Hayden Planetarium with all of the different stars, I didn't talk about that, but the people sitting in the audience, those were all astronomers. So that picture was actually from an astronomy research session. So they were using the dome to do their research to see, oh, we have this cluster of stars that are moving together that we didn't see before, which you can only really do in a good 3D environment. So yes, I mean, emphatically yes. But then you can also do like educational outreach with this. That's the whole goal that we're trying to achieve, to do the research and the education at the same time. Yes? If we can show the entire universe, we can also show different supernovas. I don't think I have any data sets about it yet, but they exist, and we could show them similar to how we show all of the galaxies. The galaxies here, we would be able to show like where a supernova exists and also go over thousands of years and actually show in time where they exist, because there's a couple of ones that we have discovered before. Yes? How much money? Oh, my personal salary? I would have to look it up. It's academia. It's not that great. It's in the vicinity of 45,000 crowns. But it's also like I've been in school constantly for the last 15 years. So that there's opportunity cost with the amount of salary I could have gotten. But I can recommend it to everyone. Like the nice thing with academia is that if you find something that is interesting to you, like you're not actually working a day in your life because it's all fun. Like it's this, like the stuff that I was just doing here, like this is my day job, right? Like this is not like work. It's like it's hard to how to express that. And it was, yeah. Okay, sorry.
Thank you so much.